The second example of factoring a difference of squares will be slightly more complicated. We're still going to factor. You'll notice the reason this one is slightly more complex is because there's some more coefficients in here. Just like before, we're looking for perfect squares, so we should be encouraged because we see a 4 and a 25. So we need to find something squared that gives us 4x to the 10th and something squared that gives us 25. By looking at the square roots, we can see that 2x to the 5th and 5 will both work. So 2x to the 5th will be the A part in the pattern, and 5 will be the B part in the pattern. Now we just fill in the pattern. So 2x to the 5th and 2x to the 5th, and then 5 and 5. And once again, we can check it by distributing it back out. Therefore, the factored form of 4x to the 10th minus 25 is 2x to the 5th minus 5 times 2x to the 5th plus 5. An important consideration is to make sure we only use the pattern when it actually works. Take a look at these three expressions and think about why they are not differences of squares. Pause the video while you do this. Even though 4 is a perfect square in the first one, x to the 5th is not. Unless you want to start using fractions in your exponents, which we'll get to later by the way, this is not going to be a perfect square. For the second one, even though we have an x squared, which is a perfect square, and we have a 4 that's a perfect square, the coefficient of 3 in front of the x squared is not a perfect square. And again, unless you want to use square roots in your factoring, this is not going to follow the difference of squares pattern. Finally, the last one is unfactorable. It's not a difference of squares, it's actually a sum of squares because of the plus sign. Sums of two perfect squares will never, ever be factorable. Think about why that is. If you recall that factoring is a way to help us easily see the zeros, x to the 4th plus 25 is like x squared plus 25, where the graph lies entirely above the x-axis, which means that it's going to have imaginary zeros. So again, you actually could use the difference of squares pattern here if you use imaginary numbers, but I don't know if you want to go there or not. So the last thing I want you to think about, what things should you be looking for in order to use the difference of squares pattern? Pause the video for a sec and think about what are you going to look at to know that this is something that you could do. Hopefully some of the things you noticed are that these expressions have two terms in them. You need even exponents in order for that term to be a perfect square. And then all of the numbers need to be perfect squared. The coefficient, and if there's a constant term, that as well. So now you have a difference of squares technique in your toolbox to help you factor and to help you find zeros.